In this lecture we're going to talk about iostat and netstat. Now these are not actually MongoDB specific tools, these are just Linux system tools. And what we're going to do is a basic description, give you an idea what they look like, what some of the fields mean, and why you might need them. First up we'll cover iostat. I've made this a little bit smaller, so apologies if it's hard to read, but I just wanted to fit everything on one page here. What I'm running here is the iostat command, which if you don't have it installed on your particular box, it's usually installed as part of the sysstat package. The sysstat package may or may not be installed by default, but if it's not, you can usually install it via yum or apt-get. And there's the information for this particular Amazon AMI. Gives you an idea of exactly where it's installed, things like that. Let's run iostat. Now, there's a few basic commands that you're usually going to want to pass into iostat. First of all, -x, and this is just to print some extended information. You may as well get more information while you're at it, is my basic principle here. The T option is to print out a timestamp with each printout. In a similar way to mongostat, it literally just keeps looping through and displaying statistics based on this interval, which we are going to set to 1. So every second, you might set this to 2 or 3 or 5, whichever your preferred reporting interval is, but the T will then ensure that when you go back and look at it, you can actually line this up with, say, a mongostat output or something else that you want to correlate with your iostat output. Finally, the M is just for readability. It changes some of the statistics from bytes or kilobytes into megabytes, so that's the M. So XMT1, there's plenty of other options, and I invite everyone to read the iostat man page to get more information in terms of the options here. So let's run that command. And you can see it'll keep looping throughout the rest of it. I'm just going to wait until something interesting shows up, and then we will Control-C out. So here we have examples. So you can see it's running every second, 13, 14, 15, as you'd expect. It's displaying the average CPU, and you might think that that's a little bit strange. Why is it displaying CPU information? After all, you're looking for I/O statistics. Well, the reason why is that there's often a direct relationship here, particularly under heavily loaded systems, between the amount of CPU usage and the actual I/O usage. And we'll get into that in a second when we're talking about what these individual fields might mean. At the moment, you can see that there is actually quite a bit of user CPU being used. On this host, that means that it's most likely MongoD. And if we wanted to briefly verify that, there you have it. MongoD sitting at the top of the top output, using up some CPU and some memory. So that's where that particular usage is coming from. So although there is some CPU usage, it's in user land. It's not related directly to I/O, so it's not really contributing. And you can see it's idle 55% of the time, the CPU. So not a huge amount going on there. Here's the actual I/O piece. We've only got one configured device here, XVD API1. For anyone familiar, I think that basically means that this is a Xen hypervisor presented disk, and that'll be fairly common for anyone using Xen, or indeed any of the Amazon EC2 instances, which are based on Xen. We've got requests per second, you've got read requests per second, you've got write requests, you've got reads per second, writes per second. The difference between you can request something but not necessarily actually have it happen. Then we've got to give you an idea of that in megabytes as opposed to the number of writes per second, or the number of requested writes per second. And here's where we get into some of the more interesting pieces. You've got your average queue size, which is pretty low. So if the average queue size is increasing, then it's not doing so for very long. You've got your average request size, which is 12. So this is the size of the actual request hitting disk. The average size, of course. If there's a lot of them, there may be bigger, smaller, different versions in there. Your wait time, service time, and percentage utilization. I've left these to last, but honestly the percentage utilization is probably going to be your bellwether statistic here. You're going to be looking at this first in most cases to see if your disk is actually struggling. So if your percentage utilization for the disk is, hitting 90%, 100%, even over 80%, it depends on how often and how frequently and how long it stays there. But that's going to be your first indicator that there might be an I/O related issue here. Service time has a note against it. These days, its original intent was to determine how long the particular device, in case XVDAP1 here, took to service the request once it had actually been sent to the device. There's a note saying this is going to be removed and not to pay attention to it, so I'm guessing there were some issues actually utilizing this particular statistic, but for now it is actually still in there. And then the wait time was the service time plus the time spent in any of the queues. So in other words, if this starts going up, it means that it's a combination of the disk taking some time to actually service the request plus the time that the operation spent waiting in the queue. So if this goes up, you can expect to see this go up. If the disk itself is struggling, the device behind it itself is struggling, you expect to see this go up, although as noted, this is now considered an unreliable metric. And certainly if you're seeing all of those things, you would expect to see the percentage utilization of this disk increase. Now, what sort of impact do you think a very high percentage utilization or very high wait time is going to actually, how's that going to manifest in terms of CPU? Well, generally what you're going to see is percentage IO wait going up. IO wait is the percentage of time that the CPU has spent waiting for an IO operation to complete before it can go on about its business. So when this starts to get high, you'll start to see IO wait creeping into the CPU, and so you can see how a slow disk and an overloaded disk, something with way too many things in its queue, unable to service them in time, maxed out, is then going to start to impinge via this IO wait metric on your CPU usage. And that can impact other things. Maybe you're doing a lot of sorts or counts on here, something that's CPU intensive, and then you can start to get slow. So it can have some interesting fallout. It's definitely something to have in your toolkit, particularly when you're looking at MongoStat, and in particular if you're seeing high levels in the aforementioned page faults column in MongoStat or similar. So this is certainly something you'd want to see trending over time. Finally, this percentage user, percentage nice, percentage system, IO wait, steal, and idle. You may recognize these from the previous MMS modules. These are displayed and graphed as part of the hardware tab, as are several of these stats here. So when you install Mun in Node and you collect those stats via MMS, you get some of this over time. Again, it's per minute, so the granularity similar to MongoStat is not going to be as good. So when you want to actually see exactly what's going on, you may still need to come in here and run iostat and attempt to understand exactly what's going on in terms of utilization, IO wait, etc. So that covers iostat. Why it's needed is to track down potentially a slow disk, give you a better idea of what that I/O is doing in terms of impacting your CPU, and that brings us on to the second tool listed here, netstat. Let's have a look. If you run netstat without any arguments, you're going to get a sort of an informational table about existing TCP connections, what state they're in, what the local address and foreign address is, including the port numbers, which can be helpful, but that's not what we're going to concentrate on here. What we're going to concentrate on here instead is the statistics that netstat actually exposes. And to see those statistics, you run netstat with the -s flag. Again, there's many more options to netstat. You can see routing tables, various other things with netstat. So we're only scratching the surface here, but the idea is to give you an idea of some of the information exposed in here and how it can be helpful in diagnosing problems later on. So we run netstat with the -s option. There's a lot of information included here, so I'm going to chop this down a little bit and just sort of highlight the interesting pieces, or at least the interesting pieces for a TCP-based database, which is what MongoDB is. So here's your first TCP section, right? This is going to be what we're looking for. Now the problem with netstat is that it's actually all cumulative counters in these statistics. So this is for the life of the box. So as long as it's been up, this is the cumulative counters. And so it can be basically impossible to do a snap judgment based on one netstat statistical output like this. What you're going to want to do is run this multiple times, pick out the interesting ones, and see which ones have been incrementing over time. So this is your basic TCP section, and as I mentioned, MongoDB uses TCP for just about everything. So if you're going to look for anything somewhat suspicious at the network level, you're going to be looking here in this TCP section and in one further on, which is the TCP extended section. So possibly some of the more obvious ones, failed connection attempts, if that's increasing rapidly, then you may have some issues there. Generally 7,387 for the life of process is not that high. 893 segments retransmitted. Again, 893 not very high, although it does depend on how long the box has been up. If you were to run this again in 5 minutes and see that this has increased to say double, 1,600 or maybe a couple of thousand segments retransmitted, then that would suggest that there's a lot of retransmits going on first of all, and retransmits happen in TCP when packets are having trouble getting to the far end. It needs to retransmit a segment because it didn't get ACKed on the other end, it got lost somewhere in between. So these retransmissions can be indicative of some packet loss, maybe some very high latency between the two endpoints here. So this could be a first bellwether sort of statistic, if it was increasing over time, that there might be network issues out there. Bad segments received, this is where it's actually going to fail probably the basic CRC check for the TCP. Again, this would be a very bad statistic to see incremented frequently. Would mean that there are just garbled TCP segments arriving at this host. Why that might be, could be a bad NIC somewhere upstream, it could be a problem with the local host itself, it could be just corruption on the network, something's flipping bits somewhere, but basically a very bad sign. Reset sent, less of an immediate bad sign. There are reasons to send resets for particular things, but again, if this is going up a lot, that means that something is triggering your host to send lots and lots of TCP resets. That might be expected behavior, then again it may not. So really what we're talking about here is that these last three are the ones that you're going to be looking at and determining if it goes up over time. Just to show you, I've run the command again. As you can see, 894 segments retransmits is not going up a lot. There was several minutes between running those two commands, and these haven't gone up a lot. So they're not incrementing in a way that would suggest that there is a problem, which is understandable. This is not a problematic host, but if they were, that would be your first sign. Once you've kind of gotten the suspicion that there's a potential issue on the network, you can look for further clues in this TCP extended section. And again, a lot of this is included on the man pages, and you can do further reading out there. I'm just going to highlight a couple of the potential common ones that will raise a flag, and you'd certainly be looking to see if they're going up. Fast retransmits is one. Definitely one of these things that you want to keep an eye on. You don't want to see this incrementing significantly over time. There's 10 times recovered from packet loss due to SAC data. SAC is selective ACK, but anywhere that mentions packet loss is not great. Selective ACKs allow you to recover from a packet loss scenario without having to retransmit the entire payload. So this is a somewhat cryptic message, but again points to potential for packet loss here. 821 other TCP timeouts, 6 connections reset due to unexpected data. That's a little strange. You don't want to see that increasing too much. You might be under some sort of attack. 10 connection resets due to early user close. No, that's not so much of a problem. 4 connections aborted due to timeout. Again, this is something you'd want to keep an eye on. But really, you're going to be looking at these retransmits, fast retransmits, retransmits and slow starts, and other TCP timeouts as a way to kind of indicate where this might be going wrong. So if you run netstat-s, you discover that there are potentially red flags in your top-level TCP statistics and perhaps in TCP extended statistics. What do you do? The most common answer to that is you contact your network operations team, or in the case of, say, Amazon, you'd be contacting Amazon to ask them about, are there any known issues with packet loss or any known issues between availability zones? I have this host and that host. I seem to be seeing issues. But the other thing that you can do is do some basic testing. You can use the sort of standard tools for testing, assuming that ICMP is unblocked. You can do trace routes, you can do pings, and of course you should be able to see in things like the MongoDB shell if there's slowness, if there are connections actually dropping out. So these are your first indicators. These can be good indicators of a problem. You can do further testing then to actually determine where that problem might be. And that covers our iostat and netstat, just a brief basic description about some of the things you might look at, some of the things that we've generally asked for when we suspect there is an I/O bottleneck or a potential networking issue out there. So these are sort of good bellwether stats, good initial indicators, and give you a very informed basis for further investigation.